In this video, we're going to talk about solutions and a few properties of solutions and calculations involving solutions. But first, to define a solution is a homogeneous mixture. So recall, homogeneous means that it's completely uniform. You cannot see all the individual parts that are in that mixture. And some other new terms, solute and solvent. So a solution is composed of a solute, which is the thing dissolved in the solvent. So an example of a solvent is water. Usually we dissolve things in water quite often, like salt dissolved in water or sugar dissolved in water. In those cases, the salt or the sugar would be the solute, and then the water would be the solvent. And then together, we call them a solution. Now, most common type of solution that we'll see anytime we're talking about the concentration of something or the molarity, that's a solution using water. But solutions exist in all three physical states technically. So if we had two gases mixed together, like air is a solution, it's multiple gases. It's mostly nitrogen, but we have other gases like oxygen and argon. We could have a solution where it's liquid and gas, so any humidity that's in the air, water vapor that's in the air, you could argue that that's a liquid and a gas mixed together. We could have, gas and liquid, liquid, solid, liquid, so any of these. Any case where you have essentially something dissolved in something else, we can call it a solution. So things that are dissolved in solution, we'll talk about gases first, but when gases dissolve in solution, how much of that gas dissolves can depend on two things. First off, temperature can affect the solubility of the gas, and also pressure. So on the next slide, we'll talk about how pressure can affect the solubility. But essentially, the higher the temperature, the lower the solubility of the gas. So if you increase the temperature, more of that gas might escape the solution. And if you bring the temperature down, you can get more of the gas into the solution. And that's the trend that we're seeing in this chart here. At lower temperatures, like at 0 degrees C, it says 0.348 grams. So that's the largest value in this chart here. We can get more CO2 dissolved in water if we just decrease the temperature. So the example that they have, if you pop open a cold soda can, you get fewer bubbles that effervesce up if the can is really, really cold. Whereas if the can is warm, more of those bubbles are going to suddenly escape when you pop open the can. The other thing that can affect the gas solubility, how much gas can dissolve in a solution, pressure. So pressure also influences the solubility of gases, and this is essentially called Henry's law, but it's saying that the solubility of a gas is directly proportional to the pressure. So specifically the partial pressure of that same gas above the liquid. So what we mean by that, here's our little soda can, and here, pop the top, and inside the soda can, mine's not really full all the way, but you have your liquid, your soda, and then you also have this, what we call headspace. So it's a little, there's a little bit of air above the soda that's actually in the can. So you could have CO2 dissolved in liquid, but then you can also have CO2 in the air above that liquid inside that can. So when they say partial pressure of the gas above the liquid, they're talking about the CO2 that's there in that headspace. And then the CO2 that's dissolved would be the CO2 that's down here actually in the soda. But what happens when you pop open a soda can? These things are, when soda cans are manufactured, there's a really, really high pressure inside that can. And as soon as you pop it open, you're releasing that pressure. So it's kind of like the pressure quickly drops from some high number to atmospheric pressure when you open up a can of soda. And then notice what happens to the solubility. It drops. So that's another reason why when you open up a can of soda, you get a whole bunch of bubbles coming out, because the pressure dropped, and now the solubility of the CO2 in your soda can is suddenly much less than it was a moment ago. So we could actually use Henry's law to calculate. The pressure is directly proportional to solubility, so we can use a simple formula, pretty much the original solubility divided by the original pressure, multiplied by the new pressure, we can get the new solubility. So here's an example. It says, what is the solubility of oxygen gas at 25 degrees C? So we're not going to use the temperature in our calculation because it's staying constant. It has a partial pressure of 1,150 torr. if the solubility of oxygen is 0.00414 grams per 100 milliliters and the pressure is 760. So this is our original solubility and this is our original pressure. So there's our original solubility and then the original pressure. And then they're saying, what is the solubility? So that's what we're solving for. And here's our answer of the oxygen gas at 25, where the new pressure is 1150. So the 1150 went in the numerator. But that's just an example of how we can use Henry's law to calculate the new solubility from an old one, provided we know the pressure before and after. Now, moving on to liquids in solution. We were talking about gases a moment ago. Now, liquids in solution. When two liquids make a solution, we'll call the two things solute and solvent. So the solute is technically whatever is in a lesser quantity, and the solvent is whatever is in a greater quantity. So for example, if we had ethanol in water, and it was a pretty strong drink mixture, like something you might buy from the liquor store, and the ethanol was, sorry, can't spell today apparently, ethanol. Let's say the ethanol was like 40% and the water was 60%. So in this mixture, the ethanol is in lower quantity, so we're going to define the ethanol as the solute and the water as the solvent. But what if you pick up a stronger bottle of alcohol where the ethanol is 60% and the water is 40%? So now the ethanol is in greater quantity, so the roles are reversed. Now technically the water is the solute and the ethanol is the solvent. They're both solutions regardless, so maybe make flashcards if necessary, but the terms are solute is what's being dissolved, solvent is whatever's in greater quantity, and then together they make a solution. Now in terms of what can dissolve in other things, we need to define this term net dipole. So polar molecules will have a net dipole. So here, these arrows, these are representing the dipoles. So these two arrows shown in the water molecule on the left, that's showing the dipole between this oxygen and hydrogen. So these two atoms have a difference in electronegativity. So the covalent bond that's in here is going to be a polar covalent bond. And then we represent that polarity using an arrow that looks like this. And it's basically a dipole, and then there's one just like it over here. Now the net dipole for the molecule, it's kind of like a combination of those two arrows, and we get something that looks like this. So what that means is over on this side of the molecule, it's a little bit more negative, and on this side of the molecule, it's a little bit more positive. So the fact that water has this net dipole, that makes it a polar molecule, and it has strong implications for, quite frankly, life on Earth and how molecules dissolve in water. So we're going to look at that and moving forward. We were just talking about water being polar, but you can also have nonpolar solvents. So water is a very common solvent. It's polar, so we would call it a polar solvent. Any liquid composed of polar molecules could be a polar solvent, and water is a polar solvent. But we can also have nonpolar solvents. So a molecule that has, it's mostly like all C's and H's would be nonpolar. So these are, for the most part, so CCl4, that one's also nonpolar, but that's a tetrahedral molecule with all chlorines all around. It's nonpolar. These are generally nonpolar, but one trend that you might notice is that all of these have oxygen in them. So this little note here is saying how general rule that oxygen containing compounds are generally polar solvents. There are a few exceptions like this ethyl ether. Ethyl ether kind of looks like this. It's got a CH2 and a CH3, and then on the other side another CH2, CH3. That's a rough drawing of what it looks like. And then of course there's lone pairs in the oxygen. But the key idea is that solvents come in two classes. You can have polar solvents and you can have nonpolar solvents. Now, there's a rule that we call like dissolves like. Polar solvents will dissolve other polar molecules. So polar molecules like to buddy up with polar molecules. And then nonpolar molecules can buddy up with nonpolar molecules. So polar is attracted to polar. Nonpolar molecules are also attracted to other nonpolar molecules. So nonpolar solvents can dissolve in one another. And we call this like dissolves like. So if two molecules are polar, they're kind of like each other. They like to talk to each other. They like to dissolve with each other. Counter examples, so like methanol. Methanol looks like this. The point is it has oxygen in there. It's polar. But hexane kind of looks like this. It's all carbons and hydrogens. So the point is that there's no oxygens in there. It's generally a nonpolar molecule. But they're not going to dissolve in each other. So that's a counterexample of like dissolves like. Hexane, so I just drew a hexane. It dissolves in something called toluene. So toluene also it's got like 7 carbons, and they kind of form a ring structure. So I'm going to draw a new way of drawing molecules, and it kind of looks like this. This is, if you ever take organic chemistry, you'll see molecules drawn this way, but it is also just all carbons and hydrogens. It's nonpolar. So water does not dissolve in toluene, but something like hexane would dissolve in toluene. So another term, miscible. So this term is pronounced miscible, but it's basically kind of like mixable. They mean saying mixable is saying the same thing as miscible, but we'll say that 2 liquids that can completely dissolve in each other are miscible liquids. So a counterexample would be oil and water. You could say like everyone knows oil and water doesn't mix, but the reason oil is generally nonpolar. So again, here's all those C's and H's in that oil layer on top, and then we have water on the bottom. Water is polar. These two don't mix. The like dissolves like does not apply here. These are not like each other. We got polar on the bottom and nonpolar on top, so they're not going to mix. So we say they're immiscible. 2 liquids that are not miscible in each other are immiscible liquids. And pretty much the common example is just like anytime you've got like oil and water or some nonpolar liquid floating on top of polar water is the most common example. Polar water and nonpolar oil are immiscible. And you'd see this anytime you have like a puddle on the ground. So, it rains, monsoon season, it rains a bit on the street. You might start to see a little bit of oil slick from the cars. That's exactly what's happening here. You have oil from the cars, any little drop of oil, it starts to, they'll collect on the top of the water, and it forms a really, really thin layer as it spreads out over the water puddles. And that's what you're seeing is the oil on top of the water because those things don't mix. They're immiscible. So next, solids in solution. We talked about gases, we talked about liquids, and now solids. When a solid substance dissolves in a liquid, the solute particles are attracted to the solvent particles. So new interactions are forming. That's when we say they're attracted to. It's basically new Coulombic attractions. When a solution forms, the solute particles are more strongly attracted to the solvent than to each other. So this is essentially the reason why a salt will dissolve in water in the first place. When the salt is a solid, like NaCl, when the salt is a solid, the sodium and the chloride are attracted to each other. But as soon as you put sodium chloride in water, now the water molecules are going to be strongly attracted to the sodium and the chloride respectively. And we're saying that interaction between the water molecules, I'm drawing some terrible water molecules here, but that interaction between the water and the chloride and the water and the sodium is a stronger attraction than the attraction we had between sodium and chloride by themselves. And that's why sodium chloride dissolves in water in the first place. But we can also just predict whether solid will dissolve by using like dissolves like. So solid doesn't have to be anionic salt. A solid could be like, a piece of lard or something. Lard is generally, it's like a fat, might be obtained from animal fat, but it's also nonpolar. It's just like an oil, and it's not going to dissolve. And that would be the like dissolves like, helping us to predict that, because oil, lard is nonpolar, water is polar, so those two are unlike each other. So like dissolves like for solids, essentially we have like three different categories. So ionic, which would be like sodium chloride, what we just said, sodium chloride, polar compounds, and nonpolar compounds. So nonpolar compounds, I just use the example of lard. They've got an example, naphthalene, and notice the formula, it's just C's and H's. So you could imagine what that structure looks like, similar to other C's and H's molecules we've seen. But nonpolar solids are not going to be soluble in polar solvents, just like water, but they could be soluble in nonpolar solvents like hexane. Polar compounds, so like table sugar, and notice that we've got oxygens in the formula, so probably going to be polar. Just looking at the formula, it's probably polar. They will be soluble in polar solvents, and then insoluble in nonpolar solvents like hexane. And then the ionic compounds, we just talked about how those work. The sodium and chloride, those break up into ions, positive sodium and negative chloride. And those will be soluble in polar solvents, again, because the polar water molecules are attracted to the sodium and the chloride respectively. But nonpolar solvents, because they don't have any like charge within, they don't have a dipole moment. So you can going back to that water molecule that we saw. They had the big water molecule here, and then they drew the dipole moment going through the middle. Nonpolar solvents don't have a dipole moment, or they don't have a net dipole like that, so they're not going to be attracted to ions like sodium and chloride. So another type of mixture that we can have, something called a colloid. So why are colloids interesting? So here we've got two beakers, one full of a nice clear solution, and here it's a little bit cloudy. So the question is, why is the beam of light not visible in the solution on the left, but it's visible in the solution on the right, which is a colloid? So this is a colloid on the right, and the colloid is essentially a solution with particles that are pretty large, relative to water molecules and other things that can dissolve. The particles dissolved in the colloid are pretty big. Now, pretty big meaning 1 to 100 nanometers. So nano is 10 to the negative ninth. So 10 to the negative ninth meters, that's pretty small for us. But when you're talking about comparing it to like water molecules or sugar molecules, that's actually pretty big. So what's happening is that the solute particles, these large solute particles that are dissolved, they're just large enough to scatter the light. And this phenomenon is known as the Tyndall effect. But it's essentially why you get cloudy solutions, or why you can see light beams or light flowing through a cloudy solution, or why a solution is cloudy in the first place, is because you have large particles, relatively large, that are scattering the light. So next, the actual dissolving process. So what happens when something is dissolving? There's essentially three things that need to occur. Number one, we have to break up the crystal lattice. So when a sugar crystal, for example, is placed in water, the water molecules attack the crystal and begin pulling it away. So we have to rip apart that structure that the solute has. And then we also the water molecules themselves have to separate a little bit to make room for the solute particles. So here we've got the sugar molecule in between four waters. So the waters before the sugar was in solution were all clustered together. They have to separate a tiny bit. And then the third thing is, of course, new interactions are formed between the sugar molecules or the solute particles, whatever they are, and the water molecules themselves. So it's kind of like a three-step process. So here's another example with sodium chloride. The first one we had sugar, which is a covalent compound. It just kind of stays as one unit. With sodium chloride, it breaks up into two, sodium and chloride. But when sodium chloride crystal is placed in water, the water molecules attack the edge of the crystal. And same thing in an ionic compound, the water molecules will pull away, they're pretty much separate the particles from each other. So in this case, separating the positive sodium ions from the negative chloride ions. And then the anions get surrounded by the positively charged hydrogens. So here's our water molecule. We're saying that this side of the molecule is a little bit positive, and then this side of the molecule with the oxygen is a little bit negative. So the anions, the negative ions, so chloride in this case, would be, they're kind of like attacked or surrounded by the positive H's. So that's why in the drawing, that green chloride, it's got the white hydrogens right up next to it because they're literally attracted to it. You got negative attracted to positive. Negative chloride attracted to the positive H's. And then the opposite is true for cations. So the cation in this example is the sodium. Cation is a positive ion. It'll be surrounded by the negatively charged oxygen. So that's why over here, that purple sphere, that's your sodium, and it is being surrounded by water molecules, but now the red oxygen is oriented, if you guys can see that. The red part of the water molecule, red being the oxygen, that's oriented towards that positively charged sodium ion. So another thing that's useful to know how to calculate for solutions is called mass percent, or they've got mass percent, but if we say just mass percent, we're usually talking about mass divided by mass, but concentration essentially tells us how much solute is dissolved in a given given quantity of solution. And we'll often we hear somebody say, dilute or concentrated, but if we want to be more specific, we could either express the concentration as a mass percent or as a molarity. So we're going to go through example calculations for both of these, mass percent and molarity, in order to express how concentrated a solute exists inside of a solvent or inside of a solution. So mass percent compares the mass of the solute to the mass of the solvent. So mass percent, sometimes abbreviated this way, it's the mass of the solute dissolved in 100 grams of solution. So that's the standard, is we express it in terms of per 100 grams of solution, because remember, anytime you do want to convert a number into a percent, where you multiply by 100. So here we're going to imagine, how much solute per 100 grams of that solution. So our formula, generally a mass of solute divided by mass of solution, which, remember, a solution is composed of solute plus solvent. So you need to know the grams of your solute, and you also need to know the grams of your solvent so that you can get grams of the solution total, and then multiply it by 100 to get your mass percent. So example, a student prepares a solution using 5 grams of sodium chloride, and they dissolve it in 97 grams of water. What is the concentration expressed as a mass percent? So 5 grams of sodium chloride, that's our numerator. And then in the denominator on bottom, we want the mass of the solution. So that means 5 grams of the solute plus 97 grams of the solvent. That sums up to 102 grams. So then we do 5 divided by 102 times 100, and we get 4.9%. So now that we have this 4.9%, we can use this in multiple ways as a conversion factor. If we had to, calculate, how much salt was in, 1 liter of this solution, or how much water would we need to add, any type of question like that, we could express this 4.9 mass percent in multiple different ways. So here it's 4.9 grams, 4.9 grams over 100 for the solution, or flipping that upside down, or we could express it in terms of water. So 5 grams of, I just realized, why does it say 4.9? This is a typo. That should say 5. 5 grams of NaCl over 100 grams of solution. No, wait. No, it's not. No, that's not a typo. Sorry. That's correct. This is correct. And then this is just expressing that same ratio just in terms of water if you needed it. So it's just multiple ways of taking this 4.9 mass percent and then setting it up as a fraction if you had to do a dimensional analysis problem where you're just converting units. So just a quick example of how we could use that. So now I have all these lines on my slide. I want to erase them. There we go. What mass of 5 mass percent of dextrose. Okay, so dextrose is a type of sugar. We have a little schematic here, like a ball and stick model. What mass of 5% solution of dextrose contains 25 grams of dextrose? So pretty much like how much solution do we need if we want to deliver 25 grams of dextrose, if we want 25 grams? So we want grams of the solution, we have grams of dextrose. So 25 grams, we just write what we first have, what the information that we know 25 grams of dextrose. 5% by mass means 5 grams of dextrose per 100 grams of solution, which is the conversion they're using here. They just flipped it upside down because we want the units to cancel. So notice they've got grams of dextrose canceling with grams of dextrose. So that's why they put the 100 on top and the 5 on bottom, just to get the units to cancel. So we end up with our units as grams of solution, which is what we wanted to solve for, and we get 500 grams. Another probably more common unit that we'll use, so molar concentration. Molar concentration or molarity, and it's important that you use capital M because lowercase m is something different. Lowercase m is actually molality, which I don't believe we're going to cover in Chem 130. Capital M is molarity, but it's the number of moles of solute per liter of solution. And we always express it as moles per liter. So moles of solute per liters of solution, usually moles of solute per 1 liter of solution. And it is the most commonly used unit for concentration. So the mass percent we're not going to use very often. Molarity is used all the time. Moles of solute per liter of solution is important to remember. So to calculate molarity, here's an example. It says, what's the molarity? We've got 24 grams of sodium hydroxide in 0.1 liters of solution. So again, molarity was moles per liter, not grams per liter, but moles per liter. So we need to convert grams of NaOH into moles. And here, this is the molar mass. It is a shame they're putting a capital M right here. I like to do double M for molar mass. Molar mass of NaOH is about 40 grams per mole. So that's what we're going to use right here to convert grams to moles. So the first thing they did is they set up kind of getting ready to calculate molarity. We've got the amount of the NaOH, 24 grams, divided by the liters. The only problem with this is that we want moles, not grams. So then they use the molar mass with grams on the bottom so that it cancels. And this is the molar mass of NaOH, 40 on the bottom, 1 on the top. So in your calculator, you would just do 24 divided by 0.1 and then divided by 40, and we get 6 molar. So we would say the concentration of this NaOH is 6 molar. 6 molar. So another example problem says how many grams of this K2CR2O7 are in 125 milliliters of 0.15 molar K2CR2O7. So we want to figure out the mass because they said how many grams. We have milliliters of the solution and we also have the concentration. So the concentration, because it's moles per liter, is essentially a conversion factor. The 125, that's just how much we have. So we're going to start with 125 and then we're going to use the concentration as a conversion factor. So one of the first things that they did was, see it says 1,000 milliliters. So remember that 1,000 milliliters is the same thing as 1 liter. So 0.15 moles per liter is the same thing as saying 0.15 moles per milliliter. They did that because here we had milliliters and we need to make sure our units cancel properly. But then the next thing, so once you use molarity, you're going to have moles. But the problem said how many grams. So that's what the 294.2, that's the molar mass. So this is the molar mass of that K2CR2O7. So milliliters cancels with milliliters here. Moles of K2CR2O7 cancel with moles here from the molar mass. And then we end up with units that are grams of K2CR2O7. And we should get 5.52. So another molar concentration example, what volume of 12 molar HCl would contain 9.15 grams of the HCl solute? And again, and this should be double M for molar mass, but they're kindly providing the molar mass of hydrochloric acid, HCl, so we don't have to look it up. But we want to figure out the volume because they said what volume of. We've been provided the grams. And again, the concentration, the 12 molar, that's really a conversion factor to go from moles to liters or vice versa. So starting off with 9.15 grams, we're going to use the molar mass to convert from grams to moles. And then we're going to use the concentration to cancel out the moles and give us a volume. And again, they've done that again where, now I'm just looking at the problem. They just said what volume. They didn't say, how many milliliters. They didn't require the answer in milliliters or liters. So you could set this problem up to say 1 liter right here instead of 1,000 milliliters. They mean the same thing because 1,000 milliliters equals 1 liter. That is a fact. So for this conversion, this using the 12 molarity as a conversion to go from moles to volume, you could put 1,000 milliliters or 1 liter. It doesn't really matter. But we're going to set it up like this so that grams cancels and then moles of HCl cancels when we use the molarity, when we divide by that 12. And then make sure that they're multiplying by 1,000 just so they get milliliters. But if you did this problem and got your answer in liters, then you should get 209 liters. And those mean the same thing. 0.0209 liters is the same as 20.9 milliliters. So another thing that we can do with solutions that's also extremely useful and very common is to dilute a solution. So rather than preparing a solution by every single time, dissolving a solid in water, we could prepare a more concentrated solution and then simply dilute that more concentrated solution to something less concentrated. So for example, the 12 molar HCl that we were just talking about, maybe we prepare that ahead of time and then we dilute it down to 1 molar HCl for the experiment that we need in class that day or something. So when performing a dilution, the amount of solute doesn't really change. So by amount of solute, I mean the moles of solute that's dissolved in the solution. That doesn't change. What does change is the amount of the solvent. So how many milliliters or liters of the solvent, the water, for example, that is used. The equation we use for this is MV equals MV. So specifically M1 times V1 equals M2 times V2. M1 is the initial molarity. V1 is that volume of the more concentrated solution that we are taking. It's usually it's the smaller volume, like we take 10 milliliters and then we dilute it up to 1 liter, for example. And then M2 is the new molarity, so the new diluted, less concentrated molarity. And then V2 is the new total volume. So for example, if we were taking 10 milliliters of the 12 molar HCl and we added 90 milliliters of water to that, the new total volume would be 10 plus 90, which would be 100 milliliters. So the key thing is that V2 is the total volume of the solution, not how much water you add, but the new total volume. So here's another example. We'll walk us through this one. It says what volume of 6 molar sodium hydroxide needs to be diluted to prepare 5 liters of 0.1 molar sodium hydroxide. So the 0.1 molar, that's the new, less concentrated solution. 6 molar is the original concentration. So 6 is basically your M1 and 0.1 is your M2. They said that we're preparing 5 liters of solution. So 5 liters is your V2. Sorry, I was distracted by that really thick writing. My pencil acted weird. So 5 liters is the V2, and we're solving for V1. So they said what volume needs to be diluted. So it's basically like how much of the 6 molar sodium hydroxide is needed. So plugging in our numbers, 6 for M1, 0.1 for M2, 5 liters for V2, and then solving for V1, we should get 0.083 liters, which is the same thing as 83 milliliters. So in chapter 9, when we did some chapter 9 slides, we did some mole calculations, so involving stoichiometry. So mole calculations involving chemical equations called stoichiometry problems. We can use these stoichiometry calculations to solutions. So if we know the molarity, we can convert it to moles using the concentration. And then if we have the balanced equation, so pretty much like the mole ratio between any two species in a balanced chemical equation, then we can convert moles of one substance to moles of another, and then we could use the molar mass to get to mass of that substance. And this is just one way we could use molarity and the mole ratio, or which is also known as pretty much using stoichiometry, to calculate something like the mass of a substance being produced, or how many milliliters, if we also know molarity of that. This is just one way we can make use of that. So let's do a quick example. It says, what mass of silver bromide is produced from the reaction where we have 17.8 milliliters of 0.105 molar aluminum bromide added with excess silver nitrate. So they give us our chemical reaction, and it looks like it's already balanced for us. That's nice. So we want to solve for grams of silver bromide because they said what mass? They said what mass of silver bromide? So I want to solve for grams. We were given volume of aluminum bromide. And we were also given the molarity, but remember, molarity is kind of like a conversion factor to go from moles to liters or liters to moles. So we're going to start off with what we were given, which was a 17.8 milliliters of the solution. Next, they're using the molarity to convert from milliliters to moles. And again, they're putting it in terms of per 1,000 milliliters, and that's perfectly fine because they have milliliters right here. So you're free to express the molarity as per 1,000 milliliters or per 1 liter, whatever is most convenient for you in the problem. Next up, this is the mole ratio between the two substances that we were talking about. So again, just kind of looking at the problem one more time. They said what mass of silver bromide, so that's what we need to get to. And they gave us information about aluminum bromide. So here's the aluminum bromide, and here's the silver bromide. So we're looking at the coefficients for those two things in the chemical reaction, which is a 3 and a 1. So that's why they have a 3 and a 1 here for the mole ratio. 3 on top because we want to try and get to silver bromide, and 1 on bottom because we want to cancel the aluminum bromide. And then the last thing here, they're using the molar mass. So if we just quickly take a look at our unit, so milliliters cancels, and then moles of aluminum bromide cancels here. And then we'll be left with moles of silver bromide, but we need to get to a gram, so that's why we have the molar mass, and we're multiplying so that moles of silver bromide cancels, and we're left with grams. And if you follow along and do that on your calculator, you should also get 1.05 grams of silver bromide.